Welcome to the Deep Dive. We unpack complex topics, give you the core insights.
Yeah.
Today, it's AI in healthcare. It sounds like sci-fi, but it's happening fast. Sharper diagnoses, tailored treatments, using patient info for a clearer health picture. But, big dreams hit big walls. Healthcare. It's drowning in diverse data, the tasks are complex, and privacy. That's absolutely non-negotiable. Real roadblocks. So, our mission today, explore MedGemma. It's a new set of medical AI models from Google Research and DeepMind. We want to unpack how they're tackling these exact challenges. Think of this as your fast track to understanding this new tech.
Exactly. And we're grounding this deep dive in the official source, the MedGemma technical report. It's pretty comprehensive, lays out the capabilities, how they built these models. We'll be pulling out the really key nuggets of knowledge from that report for you.
Okay, so let's start with the why. Modern healthcare. It's just a wash in data, isn't it? Diagnoses, treatments, monitoring, and it all hinges on pulling together info from, everywhere. Now, these general-purpose LMMs, the big AI models, they're capable, sure.
Yeah.
But for medicine specifically, where do they fall short? What's the gap?
That really is the crucial question. These general models, powerful as they are, often just lack that deep, nuanced medical understanding, the kind of reasoning you need for healthcare data. They're generalists, but medicine needs a specialist, right?
Right.
And that's exactly where MedGemma comes in. It's Google's answer. A new suite of open, medically tuned vision language foundation models. Foundation model just means it's a strong base, pre-trained, ready for specific uses. And importantly, they built it on the Gemma 3 architecture, which is already known to be solid.
Medically tuned, so built for the job.
Precisely. The key takeaway here is MedGemma promises advanced understanding and reasoning specifically for medical images and text. The report shows it significantly beats similar-sized generative models. And get this, it approaches the performance of models built only for one specific task. Yeah, and it does this while keeping the general smarts of the base Gemma models, so it's not just a small step. It could really speed up how AI gets used in healthcare.
Okay, approaching task-specific performance but staying general, that's a big deal. So let's unpack MedGemma itself. What are these models exactly? How do they work?
Good question. So the report details two main models in the collection. First, there's MedGemma 4B multimodal. The 4B refers to billions of parameters, kind of like brain power. This one takes text or images or both as input, and it always outputs text.
Okay, text and images in, text out.
Right. Then there's MedGemma 27B text. Bigger model focused just on text input, text output. The report also mentions there's a multimodal 27B version too, so text and images, but it's still being evaluated more fully.
Got it. A smaller multimodal, a bigger text only, and maybe a bigger multimodal coming. But what about the image part? That seems critical for medicine. Is there a dedicated component?
Absolutely, and this is really interesting. They introduced MedSigLIP. It's a standalone medical image encoder, about 400 million parameters. Think of it as the specialized eye for MedGemma, really powering the visual understanding.
MedSigLIP, okay.
And what's fascinating, MedSigLIP on its own enables really data-efficient image classification and retrieval. And it can do it zero shot.
Zero shot, meaning it can classify images it wasn't specifically trained on?
Exactly. It uses its general understanding.
Right.
And the report claims it performs as well as, or sometimes better than, specialized medical image encoders that only know one image type, like just chest x-rays.
That's pretty remarkable. One model handling images it hasn't seen, potentially outperforming specialists. So, okay, the really big question. How do you train an AI for something as incredibly complex as medicine? That sounds huge.
It is huge. And the methodology they describe is very sophisticated. They started with the general data used for SigLIP and Gemma 3.
The base models.
Right. But then, crucially, they added massive amounts of diverse medical-specific data. For the text side, they used standard medical Q&A datasets, MedQA, MedMCQA, PubMedQA, things like that. But here's a really clever bit. They also threw in about 200,000 synthetic medical questions generated by another AI, basically.
Whoa, AI, teaching AI about medicine.
Kind of, yeah, to create more nuanced training material. And for the visual side, the multimodal data, they focused on 2D images, and the range is vast. Over 184,000 retina images for ophthalmology, 51,000 dermatology images covering like 210 skin conditions.
Wow.
A staggering 32.5 million tiny image patches from histopathology slides paired with text descriptions, plus over 100,000 2D slices from CT and MRI scans for radiology.
That's an incredible amount of data.
It is. And they were careful about quality, too. They actually removed some common data sets, PathVQA and MedVQA, because they found quality issues. That shows real attention to detail.
That's good to hear. Data quality is everything. How did they prep all these different images? A CT scan and a skin photo are worlds apart.
Good point. They standardized the image size 896 by 896 pixels. And for CT scans, this is neat. They didn't just use the raw scan, they pre-processed it to create 3 different views focusing on bone lung, soft tissue, and brain tissues. These became the RGB channels.
So like giving the AI different filters to see different things in the same scan.
Exactly. A bit like how a radiologist adjusts the view. Then the training itself had stages. First, they enhanced the vision encoder, that SigLIP 400M part, using over 33 million medical image text pairs, including all those pathology patches.
Okay, beefing up the eyes.
Then multimodal decoder pre-training, basically teaching the language part of the model to work smoothly with the newly enhanced medical vision part. And finally, post-training. This used techniques like distillation, adding more medical text and reinforcement learning, RL, using medical images paired with text. They found RL was especially helpful for making the multimodal models generalize better.
Right, so it could handle new situations that it hadn't seen before.
Precisely.
Okay, fascinating process. So after all that, the big payoff. Let's talk results. How well did MedGemma actually do on these different medical tasks?
The results highlighted in the report are quite strong. For text Q&A, MedGemma outperformed the standard Gemma 3 and held its own against much bigger models on benchmarks like MedQA, MedMCQA, PubMedQA. It even did well on MedExpertQA, which is designed to test on questions outside its main training data. Shows good generalization.
Strong on text. But images, that's often the tough part of medicine. How did it do with classifying medical images? Especially that zero-shot thing you mentioned, where it hasn't seen examples.
Yeah, that's a critical test. And in zero-shot generative image classification, MedGemma was substantially better than the baseline Gemma 3 models. And really notably, it actually surpassed much larger API-based models on classifying chest x-rays, pathology slides, dermatology images, and retina scans.
Surpassed bigger models. That's impressive. What about asking questions about an image? Visual Q&A.
Again, superior performance over standard Gemma 3 on datasets like SLAKE and VQARD. It seems the medical tuning really paid off for vision language tasks.
Okay, those are solid stats. But generating a full medical report, like for a chest x-ray, that requires more than just recognizing things, right? It needs complex reasoning, coherent language.
Absolutely. And on chest x-ray report generation, it achieved results considered state-of-the-art. But here's the kicker, the really interesting part. They had a U.S. board-certified cardiothoracic radiologist evaluate the generated report.
A human expert review.
Okay. And the expert found that 68% of reports for normal studies and 49% for abnormal studies generated by MedGemma were equal or superior to the original reports written by humans.
Equal or superior, almost half the time for abnormal cases.
Yeah. And overall, the radiologists judged that 81% of MedGemma's reports would lead to the same or better clinical decisions compared to the originals.
Wow. That speaks volumes about potential real-world impact, not just accuracy, but clinical utility.
Exactly. It's a significant finding.
You also mentioned medical agentic behavior. Can you explain that a bit?
Yeah.
How did MedGemma do in those simulated clinical settings?
Right. Agentic frameworks. Think of AI acting more like an assistant, performing a sequence of tasks, maybe analyzing an image, pulling relevant text data, synthesizing it to suggest a diagnosis, that kind of multi-step reasoning. They tested this using the Agent Clinic benchmark, and MedGemma 27B, the larger text model, performed better than the standard Gemma 3 27B. It actually exceeded the performance of human physicians on one task, Agent Clinic MedQA, and got close to much larger models.
Exceeded human physicians on a specific task.
On that specific benchmark task, yes. Though, a small caveat. The smaller 4B models seem to struggle a bit more with that complex agent framework.
Understandable. And did all this medical specialization hurt its general abilities?
That's a fair question, but the report shows only minor dips in performance on general benchmarks compared to the original Gemma 3, so it seems to keep most of its broad instruction-following abilities. Specialized, but still versatile.
Okay, these results are definitely compelling. But medicine is incredibly specialized, right? Can hospitals or researchers fine-tune these models even more for their specific needs? Or is it kind of locked in?
No, that's a crucial point for adoption, and the answer is a clear yes. The report really stresses the fine-tuning potential. Despite the strong baseline performance, you can adapt MedGemma further, maybe for a hospital-specific reporting style, or for really tough classification problems, or even new areas of medicine.
That's adaptable.
Very much so. And they showed proof. Fine-tuning got state-of-the-art results on generating MedSigLIP reports, setting a new record score, actually. And big improvements were seen in classifying tricky things like collapsed lungs on x-rays, pneumothorax, and identifying cancer in pathology images.
Okay, so proven success with fine-tuning. What about text-based tasks like digging through electronic health records?
Yes, that too. They fine-tuned MedGemma 27B using reinforcement learning on a new synthetic benchmark specifically for EHR question answering. And it showed a substantial jump in accuracy, closing the gap with the top models out there. So it definitely highlights potential for understanding those long, complex patient records.
That's huge for EHR analysis.
Yeah.
Now, going back a bit, what's fascinating here is MedSigLIP, that dedicated image encoder.
Yeah.
Feels like it's doing a lot of the heavy lifting on its own for the visual side.
It absolutely is. Its individual capabilities are impressive. They tested it on zero-shot classification, understanding images without prior examples, and also linear probe, which tests how good a starting point it is for further training.
And how did it do across different types of medical images?
Really well. For chest x-rays, its zero-shot performance was actually higher than another specialized CXR foundation model, even though MedSigLIP used lower resolution images. It even got much better, like 7% better, at spotting things like fractures, which can be tough.
Better than a dedicated model, even with lower res.
Yeah. In dermatology, it outperformed others in telling apart 79 different skin conditions. For ophthalmology, strong performance on grading diabetic retinopathy severity. And in histopathology, really solid results, close to specialized models.
So it's a versatile visual expert.
Pretty much. The key insight is MedSigLIP offers strong performance across many medical domains, all within a single model, great out of the box with zero shot, and even better when fine-tuned. It's a real powerhouse for medical vision.
So let's zoom out. If we connect all these pieces, MedGemma, MedSigLIP, the training, the results, what are the big themes, the main advantages for healthcare innovation? What stands out to you?
Well, a few key things emerge. First, this idea of specialization advantage. Medically focused models like MedGemma clearly perform better relative to their size than giant general models on medical vision tasks. Bigger isn't always better if it's not specialized.
Efficiency matters.
Exactly, which leads to the second point, efficiency and cost. This is crucial for actual use. The report mentioned a 500-fold difference in compute cost between MedGemma 4B and the most expensive model they compared it to.
500 times cheaper to run. That's massive.
Massive. It makes advanced AI much more accessible for hospitals, labs, researchers. Third, the open release is a big deal. Making MedGemma and MedSigLIP openly available gives developers predictability, flexibility. The whole community can adapt them, evaluate them, build on them. That really speeds up innovation.
Fosters collaboration.
Right. And finally, it clarifies the strategic choice. When should you use MedGemma versus a huge general API model like Gemini? MedGemma is likely better if you need a fixed, reliable model version, if cost is a major factor, if you need to run it locally or offline, if you need its specific medical image text strengths, or if you need full control to adapt it. Large API models are still great if you just need the absolute top performance across everything without those constraints, or you could even use them together with MedGemma in those agentic setups.
That makes sense. Choosing the right tool for the job. So, okay, bringing it home for our listener, why should you care about this deep dive? What does MedGemma and MedSigLIP actually unlock for the future of healthcare? What are the tangible applications we might see?
Well, this tech opens doors for several things. Medical image retrieval is one. Imagine doctors easily finding similar past cases to help with a tricky diagnosis, or researchers building study cohorts faster, or even creating better training tools.
Like a visual search engine for medical cases.
Exactly. Then there's diverse data integration, linking radiology scans, path reports, eye photos, skin images with the clinical notes, creating that much richer, holistic view of a patient. Its text abilities are strong for clinical information extraction, pulling key facts from reports and notes automatically. Think about streamlining finding patients for clinical trials, or monitoring drug side effects, or analyzing quality of care metrics saves huge amounts of time.
Automating the tedious parts of data analysis.
Right. And workflow enhancement. Fine-tuning these models to directly assist clinicians, maybe drafting report sections, highlighting areas of concern, even helping explain findings to patients more clearly.
Integrating into the daily grind.
Yeah. And finally, those agentic frameworks. using these models as components in larger AI systems that can tackle complex, multi-step clinical problems in customized ways. So to sum it up, MedGemma and MedSigLIP look like really robust, efficient, versatile foundations for medical AI. They're showing strong results across a lot of important medical tasks, both vision, language, and text only. It really pushes the envelope.
It definitely feels like a significant step, but as always with AI in medicine, the validation is key, isn't it?
Absolutely. While MedGemma shows incredible promise on benchmarks, the report itself underscores that critical need for ongoing, thoughtful validation in actual clinical settings. Benchmarks only tell part of the story. So as these powerful tools get woven more into daily healthcare, a final thought for you. What new challenges and maybe unexpected opportunities do you see emerging from this? For patients, for doctors, for the researchers pushing this field forward?